The examples in this video go with section 9.3, inference about the difference between two means, paired samples. Example 1. A sample of 5 third graders took a reading test. Then they participated in a reading improvement program and took the test again to determine whether the reading ability had improved. Following are the test scores for each of the students both before and after the program. Can you conclude that the mean reading score increased after the program? Part A. Let mu sub d denote the population mean difference after minus before. State the appropriate null and alternate hypotheses about mu sub d. Okay, to get an idea about what our alternate hypothesis is going to be, we're going to read this last statement down here. Can you conclude that the mean reading score increased after the program? Increase means greater than. So we want to know if the mean increased once the program was over with. Okay, so we're going to write our null and alternate hypotheses. The null hypothesis, H sub 0, is going to be that the mean of our differences is equal to the mean for the population there. There is actually no change. The alternate hypothesis, remember what we said, we thought that the mean of the differences is going to increase, so our alternate hypothesis is that the mean of our differences is actually greater than the mean for our population there. And so there are our null and alternate hypotheses for the test. Now part B asks us to compute the differences after minus before. So let's go back to the chart. And for each one of these, I'm going to do the after number minus the before number, and I'm just going to record it across here on the bottom. So let's see, 67 minus 59. That's going to leave me with 8. 68 minus 63, that's going to leave me with 5. 78 minus 81, that's going to leave me with negative 3. And yes, I am going to use the negative in here. 75 minus 74, that's going to leave me with 1. And then 84 minus 78, that's going to leave me with 6. All right. Part C is going to ask us to compute the value of the test statistic t. All right, now our formula for the test statistic can be found right here. This d bar, this is the mean of all the differences. The S sub d, this is the standard deviation for all of the differences, and of course the square root of n down here, n being the number of students in our particular sample. Okay, so what we're going to need to do is we're going to need to take our handy dandy calculator here, and we're going to input this data into a table, and then we're going to run the 1-var stats on it. And what we want from 1-var stats, we want the x-bar number, and we also want the S number. So we want the standard deviation for the sample, and we want the mean for the sample. So let's do that right now. And reading off my screen here, I can see that n is equal to 5, but we already knew that because they told us 5 third graders were taking the test. The mean is 3.4, and this is what we're going to call the mean of the differences there. And then the standard deviation is 4.393, and this is going to be the standard deviation for our differences right here. And these are the numbers we're going to use to try and compute our test statistics. So I have this, I now have this, I have this. Now the mu 0 we can find in our null hypothesis, and that would be this particular number right here, which now has a variable attached to it. But let's go back and look at the problem. These students are participating in a reading improvement program. Now, really what we want to know is there a difference in scores, or is there not? And we want to know if the mean of these differences is the same as the mean of the differences for all of the students in the program, or if it has changed based on improvement or not. So in other words, what I really want to know is if the means have not changed, then the difference between them is going to be 0. In other words, if I took the equation mu d is equal to mu 0, and then I subtracted that mu 0 to the other side, we would have the equation mu d minus mu 0 is equal to 0. And that would tell me, that would be, I guess, the best case scenario is that the information that we got is actually correct. There is no difference whether they use the rating program or whether they don't. And so if there is no difference, then the difference between those differences would be 0. That's a mouthful right there, isn't it? But anyhow, we would be looking to see if there's a 0 change in the mean differences, or if there actually was a change in the mean differences. And so we would be changing this one as well to a 0. And so our null hypothesis should actually read the mean of the differences has not changed, it's still 0, versus the mean of the differences is greater than 0. It has changed. Not only has it changed, but it's gotten greater than it used to be. All right, let's go and get our test statistic again. Now that we know we're going to be using this number as 0, okay, we're going to fill in our test statistic is going to be the mean of my differences. We just found that to be 3.4 minus 0, because that would be that there was absolutely no difference at all between after they took the test and when they didn't. All right, we are going to divide this by our standard deviation. Remember, this whole thing down here is called the standard error. So the standard deviation for those differences we found to be 4.393. And then we're supposed to divide that by the square root of n. And in this case, we said n was equal to 5. Now, you're going to put this all in your calculator at one time, and you certainly can. Be sure you have this in parentheses and this in parentheses so that your calculator knows how to make those calculations. All right, I am going to put this into my calculator, and I am getting 1.731 when I round this off. So my test statistic for part C is 1.731. All right, we want to compute our p-value. The p-value we conveniently can get from the ALEKS calculator, but first of all, we need to understand that we will be running a t-test on this calculator because we had to use the standard deviation from a sample. We did not know the population standard deviation. That automatically means we're going to be using the t-test. So you're either going to be using table A3 to figure this out, or you're going to be using the ALEKS calculator, and truth be told, I think it might be a little bit quicker to use the ALEKS calculator on it. Since we are running a t-test, though, we do need to know what the degrees of freedom are, and remember that's n minus 1, so n is 5, 5 minus 1, we're at degrees of freedom for 4. All right, now we can pull up ALEKS, and I said I'm running a t-test. That's going to be this one right here. It's asking me for my test statistic that I just now found. That was the 1.731. So we'll put that in here. And then the degrees of freedom, we just found that to be 4. And so there's our p-value right there, 0.079. So our p-value is 0.079. Part E is asking us, are we going to reject the null hypothesis at the alpha equals 0.05 level? And no, we're not going to reject it. And the reason we're not going to reject the null hypothesis is because our p-value here is more than our alpha value. In this case, 0.079 is actually greater than 0.05. So we will not reject the null hypothesis. All right. Now we're going to state our conclusion. Now we are not accepting the null hypothesis. All we're saying is that there's not enough evidence to refute it. Okay. So our conclusion we conclude that the mean reading score may have stayed the same after the program. So this is our way of saying that we're going to stick with the null hypothesis, but we're still not quite sure that it actually is true. We might want to do some more testing on it. Example 2, following are the annual amounts of rainfall in inches in 6 randomly chosen cities for 2 consecutive years. Can you conclude that the mean rainfall was greater in year 2 than in year 1? Part A, let mu sub d, this is the mean of the differences, denote the population mean difference year 2 minus year 1. State the appropriate null and alternate hypotheses about mu d. Well, again, our null hypothesis is going to be that there was no difference for the year 2 minus year 1 here. So we think that the mean of those differences is 0. There actually is no change between year 2 and year 1. And our alternate hypothesis, we'll get a clue from how to write this based on our problem up here. Last sentence, can we conclude that the mean rainfall was, there it is, greater in year 2 than in year 1? Well, if it's greater in year 2 than year 1, then we think that the mean of those differences has increased, and now it's going to be more than 0. So there are my null and alternate hypotheses. Part B is asking me to actually compute those differences, year 2 minus year 1, and I will write them down here underneath my chart. And here you can see I have put in all of the differences. This is year 2 minus year 1. Remember, we do want to include that negative here for year 3, or for city 3. All right, next, we want to compute the value of the test statistic. All right, now before I can do this, remember, I need to go back and I need to, in my calculator here, I need to put in my circled numbers into a data set and run the 1-bar stats on it, because I need the mean for those differences and I need the sample standard deviation SX for those differences. And I have already done that in the calculator. And the mean I get, and I'm just going to come over here. So the mean of the differences is 5.63, and it's actually 5.63333333. There are actually 6 cities in my data set, and the standard deviation for these differences is 5.283. All right, so now we can figure out our test statistic. We're going to take the mean of our differences, and we're going to subtract off 0. Remember, that came from the null hypothesis right here. We don't think there's a difference at all. And then we're going to divide this by the standard deviation of those differences divided by the square root of n. And remember, if you want to put this in your calculator all at one time, be sure you have your parentheses like this, and you should be able to do it. And this is giving me 2.610. Okay, part D, are we going to reject the null hypothesis at the alpha equals 0.05 level? Well, let's figure that out. We need a critical value. There is a number right here, so that all of this area, or probability back here, is equal to 0.05. And I'm going to have to figure out this number. This is going to come from table A.3, okay? And again, we're going to have to use table A3 because we use the sample standard deviation here, okay? That means I need some degrees of freedom. So the degrees of freedom, 6 minus 1, this is going to be 5. All right, if I want this number right here, on table A3, I am going to be looking at line 5 and column 0.05, and I'm going to try and see where those two intersect one another. And that's going to be my critical value right here. I guess I should have called that CV instead of calling it X. So let's change that. This is going to be my critical value right here. Okay, let's get table A3. All right, we pulled up table A3, line 5 right here. Reading across line 5, we're looking for where it intersects column 0.05. Here's column 0.05. So the number I want looks like it's going to be right here, the 2.015. And so let's bring that back to the picture. And I'm going to take that CV off. Actually, our critical value is going to be equal to 2.015. And now we'll take all this out of here and make a little bit of room. Okay. And what we just found out from table A3 is that this number right here is 2.015. From this point on, the area behind that line is 0.05. Okay, now part D, are we going to reject our null hypothesis or not at the 0.05 level? That's where this number came from. We got it from right here. Well, it depends. Where's our test statistic? Where does T fall? Remember, the mean as a t-score is right here. I'm sorry, even as a t-score is right here in the middle. It's always going to go with 0. Where is 2.6? Is it to the right of 0? Is it to the left of 0? Will it be to the right? Now, where does it fall in terms of my critical value? Is it to the right of my critical value, or is it to the left of my critical value? This one is actually going to fall somewhere back here. And it is contained right here inside the shaded area, or within that area there, okay? So because my test statistic is included in my shaded area, we are going to reject the null hypothesis. And then for part E, we need to state our conclusion. Since we rejected our null hypothesis, that means that we are accepting the alternate hypothesis. And the alternate hypothesis, we said, was that there was actually a difference. In fact, the difference was greater than 0. It's positive. So we can say that our conclusion, the mean rainfall was greater in year 2 than it was in year 1. Example 3, a group of 5 individuals with high blood pressure were given a new drug that was designed to lower blood pressure. Systolic blood pressure was measured before and after treatment for each individual. The results follow. Construct a 95% confidence interval for the mean reduction in systolic blood pressure. Okay, so we are going to find the differences of, let's do before minus after, so that we end up with positive numbers down here for the most part. Okay, we should get a similar solution at the end of the problem if we did after minus before, but I'm just choosing to work with positive numbers here. So I'm going to write my differences down here across the bottom, before minus after. And here you can see I have my differences across the bottom. Now remember, I'm going to use my calculator again, and I'm going to put those differences into my stat list and run one bar stats, because I am actually going to need the mean of those differences, which I have to be 31.4. And I also need the standard deviation for those differences, which I have to be 7.300, and of course n is equal to 5, and they told me that right back up here. Okay, now we need to do a few calculations because we're going to try and find a confidence interval. Since we're using the standard deviation for the sample, we do in fact need some degrees of freedom here, and so that's going to be 5 minus 1, or 4. Okay, our formula. We've got our differences in the mean. We actually need to get our critical value. This we're going to pull out of table A3. We've got our standard deviation. We just pulled that out of the calculator, and of course we know what n is. So let's get our critical value. We're going to get this out of table A3. Okay, coming over here, the critical value, and we are going to be looking at line 4 and column 95%, and we're going to try and figure out where these overlap one another. And let's see, here we are, line 4. Now notice the top does not have the percentages on there. The percentages are actually located down here on the bottom, and so we're going to need to scroll down here to the bottom of the chart to get to our differences. Okay, so here's our 95% right here across the bottom. This is 1, 2, 3, 4. This is the 5th column over. So let's go back up here to line 4. Line 4, 1, 2, 3, 4. 5th column over right here, 2.776 will be our critical value. All right, over here where I've got a little bit of room to work. The standard error is going to be the standard deviation for our differences divided by the square root of n. So the standard deviation for our differences in this case, 7.300, divided by the square root of, let's see, n was 5. All right, and let's put this in the calculator. And this is giving me 3.265. Okay, next thing we need to know is we want to know what the margin of error is. Now the margin of error is our critical value times that standard error there. Okay, the critical value we just found, 2.776. And we are going to multiply this by the standard error we've just found, the 3.265. And this is going to give me 9.064. All right, and now if I want that confidence interval, I am going to take my point estimate, in other words, the difference here, 31.4, and I'm going to subtract off that margin of error, 9.064, and I'm also going to take that difference mean, and I'm going to add the margin of error. And here are the numbers that I get when I do the subtraction and the addition. Now when I go to write my confidence interval, I'm going to round this to the first decimal spot here, so I'm going to call this 22.3 to 40.5. And we're going to go with this to be our confidence interval. Example 4. The statistics department at a large university instituted a program in which students could get extra help with statistics in the evening. The following table presents scores for tests taken before and after the program for a random sample of 6 students. Construct a 99% confidence interval for the mean increase in test score. Okay, so the first thing I want to do, I guess, is calculate these differences, and because we think the test scores have increased, I'm going to do after minus before, so I'm going to write those down here across the bottom. And I am going to take all of these numbers right here, and I'm going to put them in my calculator, and I'm going to run the 1-bar stats on them. And I'm going to go over to another screen and have a little bit more room here. Okay. All right. Things that we know. There are 6 students involved here. The mean of the differences is 6, and I'm pulling this off my calculator. The standard deviation for those differences is going to be 2.280. All right. Since we're doing a confidence interval, and since we're using the standard deviation not from the population but from the sample, we do know we're going to be using table A3 again, so I do need some degrees of freedom here. And the degrees of freedom will be 5. We need to go and get our critical value. The critical value is coming off of table A3. And we will be looking on line 5 and column 99%. Yep, 99% here. All right, so let's pull up table A3, line 5, column 99%. Okay, let's figure out which column is 99% first. Okay, that's going to be this one right here. So we got 1, 2, 3, 4, 5, 6. This is the 7th one over. Okay, now let's go up to line 5. 1, 2, 3, 4, 5, 6, 7. It looks like our critical value here, 4.032. Okay, let's see, the standard error. We said this was going to be the standard deviation, 2.280, divided by the square root of n. All right, and in my calculator, this is giving me 0.931. The margin of error, our MO, this is going to be our critical value, 4.032, times the standard error we just found, 0.931. And this is going to give us 3.754. And so our confidence interval is going to be the mean, which was also 6, minus the margin of error, and then the mean plus that margin of error. All right, and so this gives me a confidence interval between 2.246 and 9.754. When I report my confidence interval, I'm going to round this to the nearest whole number. So this is going to be between 2 and 10. And the reason I'm doing this is because in the context of the problem, we are in fact talking about points on a test. And not a whole lot of professors will grade and give you half a point or a quarter of a point or whatever on your final grade. Most of them round it up to the nearest whole number. And so I'm rounding these up to the nearest whole number as well. And our confidence interval will actually fall between +2 and +10 points.